Thank you for this nice introduction. It's a pleasure to be here in Berlin. And I guess just needs focus. Again? Okay, perfect. That's good. So, why we are interested in vertical routing? Vertical routing is among the most widely studied form in combinatorial optimization, essentially because it's a very practical problem. So every company that has to perform the deliveries from a grocery store to Amazon, they have to solve vertical routing. So we have many papers published every day. And okay, but the real vertical routing problems are many variants of the problem depending on the characteristics on that system. So the most classical we have capacities, vertical capacities in terms of wave, volume, so on. We have time windows, the times where the customers can be served. We have sticking to the laptop, otherwise the mic will pick you up. Okay, sorry. My apologies. Have a heterogeneous fleet. So in this case, we have heterogeneous fleet. We have multiple depots, split delivery, pickup and delivery, backhauling. We have a whole family of routing problems. The arc routing, for example, garbage collection or snow removal, where instead of visiting particular points, you have to traverse all the streets in the neighborhood. And now we have those emergent variants like electric. What's the difference between electric vertical route and traditional? Is that electrical vehicles, they should be recharged during the day. They cannot work 24 hours without recharge. And this recharge is slow, and the curve of recharge is non-linear, so there are particularities. And then we have drone routing, warehouse routing. But let's start with the most famous problem in NP-hard problem combinatorial optimization, TSP. TSP is a VRP, so it's a VRP for a single vertical. And we have this formulation here, the classic formulation by Densky, Fulkerson, Johnson. So we have here that the route should enter and leave the point. And we have here the structure elimination. And how about the optimal solution of TSP? So in 1954, Danzig, Fulkerson, and Johnson could solve 49 cities. This was amazing for the time, the computers that they have. And only in 1971, people could solve larger instances. Then in 1977, with the work of Groucho, it started the idea of doing polyhedral analysis, of finding families of facets of branch and cut, and the results. And here, so we have this curve here. So this is the size of the maximum instance that can be solved. So up to 85,000 points by Concord code. So it's a very big success. And okay, it took 135 years of CPU time to solve that. This isn't, but the most interesting thing is that typical instance with 1,000 cities are now solvable in minutes. So for most practical purposes, TSP can be solved to optimality. And so this is a big success of this idea. So you formulate the problem, you do in the natural space of variables, you investigate the polyhedra, and you divide separation procedures, and you have a branch and cut. Okay, so and many people believed that this could be done for other problems too, and actually they try to do that on vertical routing on CVRP, the most classic variant. For CVRP, we have the set of values, and the values are capacitated. They have capacity Q. The customers have demands DI, and the sum of the demand of the customers in the same route cannot exceed the capacity of the value. Okay? And we have a formulation that's quite similar to the TSP formulation. Where in this formulation, we have a degree. And here we have those constraints. If you take a subset S of the customers, you sum the demand, divide by the capacity, round up. This is a bound on the minimum number of values that should visit that set. As the value should leave and enter and leave, this is multiplied by 2. So we have a very similar formulation. And many people, they try to emulate what had been done on TSP. So they start to study this polyhedra, and they found many families of facets. So framing capacity, strengthened multi-star. Some people are even the same people that studied TSP, studied CVRP. So many branch and cut algorithms were proposed in this time, but the results were not good. So even with a very advanced branch and cut, very advanced, around 2003, 2004, there was an open instance with 49 customers. Remember that 49 cities was solved by Danzig in 1954. So it's very small. So, and why this? What's happening here? No? The problem is the gap, the root gap. So even with all those inequalities, we have quite large root gaps leading to very large branching boundaries. So what's the difference? If you take the structure formulation along, the gaps are already quite small. If you separate the blossom cuts or two matching cuts, you already get like this. And if you separate the other, so hypertour, domino, parity, many things, you get, I'm putting 0.05, but actually most often 0.01%. So you are almost there, okay? On the other hand, the starting formulation for the CVRP is not so good. So we have gaps that are large. And even with the separation of very complex cuts, we still have a big gap at the root. Okay. So there was another idea to solve VRP, to solve CVRP, is that the set partitioning formulation. The set partitioning formulation, we have one variable for each possible route, and those variables together should cover all the customers. Okay. And as we have an exponential number of variables, this should be done by column generation. So the linear relaxation of this should be solved by column generation. The pricing is actually in a strongly NP-hard. If you want to separate to price routes that are elementary, this is strongly NP-hard, so people actually relax it. So instead they can, for example, price what they call Q routes, which are routes that may repeat some customers, and this makes the problem much more tractable. Okay. And many people think that the set partitioning formulation is very strong. It is not. Okay. It's strong for the VRP with time windows if the time windows are very tight. But on CVRP, where no time windows, that equivalent to very large time windows, the gaps are worse than the gaps of the branching cuts. Okay. But the idea, the first improvement got with the idea of combining both things. So let's do column generation, but let's separate cuts too. Let's combine both things. And the observation is that if you have a cut over the edge variables here, you can translate this into a cut into the route variables here. And with this, you get much better bounds, okay? And we have here this distinction. When you are doing column generation and you want to separate cuts, you want to, and you want to separate cuts, you have a new cut. This cut has a new dual variable, and this new dual variable should be taken into account in the pricing. And there are essentially two kinds of cuts. The cuts that we call robust means that the dual variable can be somehow incorporated into the cost. So the structure, the cost is in the pricing. So the structure of the subproblem does not change. And the non-robust, they change the structure of the pricing, making it harder. And so we have those two kinds. So first, initially, people used only robust cuts. Okay. And here we have the results. This is the combination of, this is only branch and cut, and this is branch, cut, and price. And the gap was reduced from 206 to 081. Does not look much, but remember that the size of the branch and bound tree grows exponentially with the gap. So all instances could be solved. But only 3 instances at the literature could not be solved. Those here, 151, 200, and 200. And since then, all algorithms, exact algorithms for CVRP, they do this combination. But so progress was done. So some authors realized that non-robust cuts could be useful even if they changed the pricing, but it was worth to use them. And another idea that was introduced was the idea of enumeration. So you solve your root node. Instead of branching, you can enumerate all routes with reduced cost smaller than the gap. And it's guaranteed that the optimal solution is inside this set, okay? So if you don't have so many routes, if you have, say, 50,000 routes, you can give it to your favorite VRPSolver and finish the optimization. So here, this work introduces the concept of indie routes. This is a relaxation of the elementary routes that's more effective than the Q routes. So you have a better quality of your bound, and the pricing is still cheap. We have this work here that proposed a family of non-robust cuts, but there are less non-robust. They disturb less the pricing. Okay. Here, this work by Hopke, he went back to robust branch, cut, and price, but people before imagined that the strong branching, so the idea that you test hundreds of candidate variables for branching was not suitable for column generation because column generation is lower. But Rupke showed no, not at all. You should do strong branching too when you do column generation, but you should do this in a smart way. And he could finally solve this instance in 5 days. Then this work here introduces some new ideas, in particular this idea of enumeration to a pool. So suppose that instead of 50,000, you enumerate 5 million routes. If you give this to Ciplex, Gurobi, Express, wherever, will not work. But the idea is that you store those routes in a pool, in a table, and you start to perform the pricing by inspection. So in this way, the non-robust cuts become robust because no matter the structure of the cut, by inspection, you can price it. And they managed to solve this instance in 3 hours. And then there is this work here that proposed the branch cut and price algorithm that combined all those ideas with some new ideas. And so it uses robust cuts, rounded capacity, strength, and comb, non-robust. After enumeration, you can use click cuts or ordinary click cuts. The most critical element of our branch cut-in price for VRP is the pricing. So it's a dynamic programming labeling algorithm. It should be very efficient and should handle the NG routes and the modifications induced by the non-robust cuts. So there's this idea of bidirectional search. So instead of doing the dynamic programming in one direction or in the opposite direction, you do in both directions and you concatenate in the middle. So this idea. You have completion bounds. So you have a state in your dynamic programming, a label that we call. If you can determine that this state cannot be extended to a column with negative reduced cost, you can already prune it. We can do fixing by reduced costs over the original variables by doing dynamic programming too. This is very important. But even with the care, the non-robust cuts that we use, they are non-robust. Sometimes it happens that we have already introduced, say, 300 non-robust cuts. The pricing is okay. Each pricing takes 1 second. It's a lot, but it's typical. And then you separate 20 or 25 more cuts, and then the pricing starts to take 1,000 seconds. Okay? There's an exponential explosion. What you do in this case, you roll back, you remove the bad cuts, okay? And you branch. There is hierarchical strong branching. There is this concept of route enumeration. There is a trick for convergence dual stabilization. Okay. And the results are much better if you compare here. So the gaps are very small. The root gaps are very small. Okay, here 0.003. So this was solved in 3 minutes, and the remaining could solve in a few hours. There were some larger instances in the literature, but they were considered to be out of the reach, but now they could be solved. For example, this golden instance here. And actually, perhaps the breakthrough in this work was the concept of limited memory cut. This is the idea is that you have a non-robust cut, and so typically in the polyhedral analysis, you want to have the cut as strong as possible. You lift the cut so the coefficients are as large as possible. We do the opposite. We unlift the cut. We reduce coefficients. So, but why we do this? To make the pricing easier, but we reduce the coefficients of the variables that are not really necessary. So in the end, you get exactly the same bound, okay? So the cut only has positive coefficients where it needs to be to have positive coefficients. So the variables that have typically large costs that will not appear in a solution, they have coefficient 0. So this makes this is dynamic, actually. We adjust, the cut is dynamically adjusted according to the current fractional solution. Okay? So this was perhaps the breakthrough. And actually, what we call now the advanced branch cut and price algorithms are exactly these, the algorithms where the pricing and the cut are designed in a symbiotic way so that they can work together very well. Okay? And the cut is already devised thinking of the dynamic programming labeling algorithm. So if the same cut was introduced, if we change the pricing, so let's solve the price as a MIP, those cuts would actually be very bad. Okay. So the cut is devised to be good for a particular algorithm. So this is the, okay, and this work was recognized here. But okay, this is CVRP. CVRP is a very simple variant. The real problems that routing problems that people need to solve can be much more complex than this. And then we started to try to expand this to other variants. So we did that for VRP with time windows, for heterogeneous fleet, for capacitated arc routing. And what we realized, it took a lot of time. So for extending what have been done on CVRP, for VRP with time windows, it took months. For extending to CARP, it took 1 year. So we would like to have one algorithm that could work in all those variants, and that's the idea. So this is how VRPSolver was proposed, was devised. So what is VRPSolver? Okay, it's a branch cut and price solver for a very generic model that is generic enough to encompass most VRP variants and many other kinds of, not many, but a significant number of other kinds of problems too. But by generic, we mean really generic, because the VRPSolver is not based on, okay, you have the concept of customer, vehicle, route. No, it's a general MIP plus, so you model in VRPSolver, you define a MIP, and you define that certain variables should be linear combinations of resource-constrained shortest path over certain graphs defined by the user. So you have a completely general MIP, and besides, you say this set X of variables here, they should be the combination of those paths. Okay, I'll give an example. So it's very generic. But let's have what are the resource-constrained shortest paths? So I will show this example. So in this graph here, we are looking for a resource-constrained shortest path over a single resource from the source to the sink. And in blue here, we have the consumption. And here we have the intervals on accumulated resource consumption, okay? So let's check some paths here. This one, is this path feasible or not? It is not. Why? So we start here, the accumulated consumption is 0. We traverse here, we consume 2 units of resource, but here the interval starts at 3, but it's okay. We can drop 1 unit of resource. So this is like in time windows that you arrive too early at the customer and you wait. So suppose that the resource is time, you arrive at too early. So it's possible to drop the resource, okay? But then you serve the customer, so your accumulated consumption is 3. And when you traverse here, your consumption is 4, you arrive here with 7, and 7 is more than 6. So this is not feasible. So this path will not be generated. What about this? This is feasible. Well, why this is feasible? It's not elementary, but this is feasible because you start here with 0. In your first visit here, the accumulated consumption is 3, accumulated consumption 4, then 5. Then in the second visit, accumulated consumption 6, 7, everything within the interval, and you arrive here with 10. So this is good. Yeah. What about this? This is good too. Another good. So the idea is that the user will define a graph, will define a number of resources. There can be many resources, okay? And defines the consumption, define the intervals, and implicitly the VRPSolver will generate paths over those graphs, and some variables in the MIP should have linear combinations of those paths. Okay, so after we define the graph, we have a mapping. So some variables are mapped to arcs in those paths. So we have this linear relation between the arcs and the variables. But so here's the model. So this is a completely general MIP in the sense that we have here a linear objective function. We have a linear set of constraints, completely arbitrary set of constraints. Some variables are integers, some variables are continuous, okay? But we have this, that the x variables, so we have x variables and the y variables. The x variables are called the mapped variables, and the y variables are the unmapped variables. The mapped variables, they should also be linear combinations of this variable. Lambda p is a variable that's associated to path, to resource constrained path p in a certain graph. So those variables x, they should be linear combinations of. And how we solve this? Actually, we substitute. We have an expression here for every variable. So we substitute here. So the y variables remain, okay? And so we have this x variables were eliminated. So we have an exponential number of lambda variables. And this should be solved by column generation. Okay? And I'll give an example. So the example is a problem that's not routing. So my example will be on generalized assignment problem. And this is the natural formulation for a generalized assignment problem. So we have variables x, t, k, meaning that this is one if task T is assigned to machine K. Okay? We have the assignment costs. We have the constraints that each task should be assigned to one machine. And we have here the capacity constraints. Those are knapsack constraints. So the capacity of each machine is not exceeded. Okay. And how we model this using VRPSolver. First, we are going to define a graph that will represent the knapsack constraints. And so the idea is that we are going to have graphs, one graph for each machine that will model the knapsack constraint over for that machine. So essentially the idea is that we have the items here, item 1, 2, 3, 4 to the last one, dummy one, and we have two parallel arcs here. When the paths are from here to here. When you use the upper arc, this arc consumes resource, okay? When you use the lower here, consumption is 0. So, and we define limits on the accumulated consumption that is equal to the capacity of the machine. So let's give an example here. For example, this route here. So here we are not including item 1 in the machine. So we are using the lower arc. We are including item 2. So the consumption is 8 because here, okay? And we are not included item 3. So this corresponding to the assignment of only item 2 to machine 1. This corresponds to assigning item 1, 3, and 4 to machine 2. Okay. So we are representing the possible solutions for each machine as a resource constrained shortest path over this graph. And here's the MIP. Well, the MIP is looks strange because here's the objective function, and here is the assignment constraints. But okay, but And the rest is implicit by the fact that those variables should be linear combinations of paths over those graphs. So, here we have all possible paths over those graphs. And so the formulation is this. Okay. So we have the objective function, the assignment constraint, and here we are saying that the xt key should be a linear combination of those paths. By substituting here, we have the classic column generation formulation for gap, and this is solved by so we have this. Okay. So variable x22 is equal to this. Why? Because those are the paths that assign job 2 to machine 2. Okay, and when we substitute, we have this. Okay. Okay. So VRPSolver was coded in C on top of BAP code package that by Vanderbeck and Sadikov. There is also a Julia jump interface. We test on 13 problems. Okay, and here we have a comparison. We have here a problem, say CVRP. This is the data set, the number of instances of the data set, the time limit, and we are comparing VRPSolver with the best published specialized algorithm for the problem and the second best. So for CVRP in the set, VRPSolver could solve all the 12 instances with the average this time. It's a bit worse than the specialized algorithm here. For this set, it was a bit better than the specialized. Then we have here VRP with time windows, multi-depot, pickup and delivery. And pickup and delivery, the results are mixed because for this class Hoppe-Cordeau instances, it could solve all the instances in 5 minutes. But for the leading instance, it performed bad, much worse than this. This is a team, real team problem. This is gap. Okay. This is gap, and for certain classes of instances, it works very well. This is vertex packing. This is classic beam packing problem. So for you have to time in. I teach my classes walking from one side to the other. I have this. Okay, and this is the classic beam packing problem. So it works well, especially on the hard instance. And this is capacitated arc routing. And well, on CVRP, we did more tests here. So the X instance on that are now on CVRP lib, and this is perhaps the state of art of exact solution for CVRP. So if you have instances with up to 200, you will solve it. Okay, perhaps taking many days in some cases. There are some, typically not, typically in minutes or hours, but some take days. If you have instances between 200 and 300, probably. Here, if you are lucky, here, very rarely. But this is the largest CVRP instance ever solved. So this is the depot. We are not represent the arcs to the depot, otherwise the picture will be too full. So what about VRPSolver? So VRPSolver is available now for academic use, but there are two ways of using VRPSolver. First, you have all the algorithms bundled in a Docker, okay? And you can use this in any platform. But this is not so good because essentially this version is stuck in 2020. It has not been updated. So even the Julia already changed. So it's an old version of Julia. There is a C++ interface for Linux, does not require. But let's tell the truth, VRPSolver at the moment is not very convenient for the users. There is no good documentation, there is no support. If you found a bug, it may take 6 months to be fixed. And so it's far worse than it should be. We're trying to fix that. And this is one of the motivations of my visit here to Berlin, is to learn what you have done here in Skip. So I'm seriously trying to open completely the VRPSolver code and create a collaborative project where people can contribute. And I liked this idea that you have that every year you publish a paper. So Skip version 9.0, it's a buzz paper because the number of authors is 31 authors, but that's okay. The idea is that everyone should be, that contributed should be author, but if you contribute with a particular feature for VRPSolver, you can publish a paper. If 2 or 3 people introduce a feature in VRPSolver, then can publish a paper with that feature. But I'm serious about trying to make this open source so people can really use it. So this is an example. This is a CVRP model using VRPSolver using the Julia interface. But in spite of all those problems, up to now, we have 45 published papers built on top of VRPSolver, 2 of them published in Operational Research. So many variants of routing and some non-routing too. So it's interesting because when you use VRPSolver, sometimes you need a lot of creativity to fit your problem into that framework. So you have to devise that graph and devise the mapping, and this is sometimes is very non-trivial. So most of the works that I mentioned here, okay, if you want to solve VRP with time windows, this is easy. You just take the demo. But for many of those problems, there are tricks, like the trick that I just showed for showing the cart. So the trick, how to represent a knapsack constraint as a shortest path, okay? So many of these works here, they use very sophisticated models on top of VRPSolver. And but we realized it too that modeling over VRPSolver was too difficult for many users, especially people, the practitioners that are not even acquainted with MIP. So we have now VRPSolverEasy, that's a Python interface. It's not fully general, but the idea is that people can represent the routing problem. So they can define the value code, define time windows, define the fleet, define the depots, if the routes are open or closed, if the customers are mandatory or you pay a penalty for not visiting. You may have parallel links connecting customers. So suppose there's a fast track, but you have to pay a toll, and there's a slow track, you do not have to pay. So you have 2 parallel arcs that so you use the fast one if you are in a hurry. So this is free for all users. So what's the impact of exact vertical routing algorithms in practice? Historically, it had been very small. So most 99.9% of the users, they do heuristic, and they have very good reasons for doing that, because sometimes the problems that they need to solve are much larger and they need the solution in seconds. Okay. But now, most classic VRPs, we can solve up to 200 customers, but there's the good news that if you can solve with 200 customers, say in one day, it means that for 100 customers, you can solve in minutes because it's exponential. So when you go down in the exponential, you have an exponential gain. So it means that typical instances with less than 100 customers are now solvable in a few minutes. And this is practical. So if you can have an optimal solution, why not? And the other problem is that the real problems that people need to solve are never CVRP or never VRP with time windows or never, but now we have something much more generic that can be, okay. So we expect that now the people will start to using the exact algorithms, at least for benchmarking their heuristics, okay? So, okay, I will use my heuristic, but let's benchmark it not in instances with size 10, but on instances with size 200 to see if the risk is good or not. And all this is based on, heavily based on column generation and this branch and price, branch cut and price algorithm. And until very recently, there were 0 textbooks on column generation. So it was difficult for students to learn about this. And now we have actually 1.5 books on it. So the first one, Marco Lubeck showed you 2 days ago here. Okay, and we released our book too on column generation. Actually, we released the first part of the book, but this first part is already can be seen as a volume 1 because it already covers all the fundamentals. It has more than 300 pages, exercises, and many things. It's more than material for a complete course on the volume 2 will present the very advanced techniques that I mentioned to you, but the basic column generation everything is already there. And it can be downloaded at this web page, but and a nice thing is that I think nice that we are setting a GitHub for creating a community of users of the book or readers of the book. So if you do not understand some part, you can ask for help and other readers know. And we observing the how, for example, the exercises. There are many exercises that require implementation. Then someone will implement in Julia, someone will implement in Python, someone will implement using Skip, someone will, and this is what we want. So the book, there is no official language in the book, so the exercises are expressed mathematically, and we expect that the readers will provide their implementations using different frameworks, different packages. We are not attached to any particular code, no, not at all. Okay, so that's it.